Hello, and welcome to our virtual presentation on advanced AC/DC power architectures for modular data center enclosures. Our technical directors are Mike Bronner and Tyler Balkzoon. I am Adam Silvestri, and working on this project with me is Alexis Noriega. We are both electrical engineering students. So a brief company overview of Electric Boat. They are located in Groton, Connecticut, and are the design yard and prime contractor for the Virginia-class submarine program. They pride themselves on being defined by their people through their skills and commitment to the company. Understanding what a power distribution system is and the criteria that are important was integral to our project. The criteria that we considered throughout this project are redundancy, availability, efficiency, cost, modernization, and power monitoring ability. So the components of a power distribution system include circuit breakers, transfer switches, uninterruptible power supplies, power distribution units, power monitoring software, cooling systems, busways or cabling trays, as well as batteries or other power storage. What makes our project unique is that we are designing a system for a mobile data center. So what makes a mobile data center than any other data center? They need to be modular and portable, all self-contained in their own enclosure. It's also very important for them to be rugged, as they will be subjected to a lot of transportation and various temperatures. Mobile data centers, as well as any other data center, require stable and reliable high-voltage DC power. Most data centers existing today are powered by three-phase AC, with conversions to DC at a component level. And below here you can see a one-line diagram of the traditional AC power distribution. Being able to have a flexible DC power distribution system is very important for next-generation servers. In our project, we will investigate, perform technology assessments, and develop simulation models for capabilities of DC power systems in a mobile data center. And below here, you can see the diagram of a traditional DC power distribution. And you can see that with conversion to DC earlier on, you no longer need individual DC conversions on the component level. Our anticipated best outcome includes identification and assessment of power distribution technology and components for our mobile data center, considering the following criteria: power distribution being DC, power monitoring abilities, modernization capabilities, as well as the technology readiness levels of technologies that we are researching. Next, we will like to provide a model giving the required power characteristics as well as component changes and upgrades that may happen in the future. We also want to create a prototype development plan that will eventually support a potential proof of concept demonstration. Now going into our team technical accomplishments, we performed some initial research on power distribution systems and became familiar with some different distribution architectures that you can see below: centralized, distributed, and decentralized, and we decided on more of a centralized system. We also narrowed down important concepts and criteria that were listed earlier in this presentation, as well as deciding on using a completely DC system, which is definitely in line with our anticipated best outcome. Next up on our team accomplishments is the research of specific components, the most important of which being UPSs, PDUs, transfer switches, and power monitoring systems. And in this research, we listed and noted most of the important features that we want in our specific components. Our final main team accomplishment is the use of technology down selections. So we have two sections here, as you can see in the red and the green. In the green section is the general design. So this is stuff like the type of voltage in the system that you can see here below, and the location of different parts of our system. And so we use this to get our general architecture and our general system structure down. Once we did that, we moved on to the red, which is our specific technology. And so we used this to analyze things such as what you can see here, battery technology, and list out a bunch of criteria and a lot of different components and technologies to see what would be best for our system. Our project has quite a significant economic impact on Electric Boat, as it will allow for improved and cost-effective DC power systems to be implemented in mobile data centers. It will also create the opportunity to reduce cost and complexities for new system integration into old existing systems. And it will also reduce overall costs in general. This is the main block diagram of our entire system. As you can see, we have two feeds of AC coming into the input circuit breaker, two feeds of AC coming out, going into the transfer switch. That transfer switch then picks one of those feeds, outputs one AC feed into the UPS, which then the power goes down into the power distribution unit, then into the rack PDU, and then into the IT equipment. In the following slides, where we give you our technical accomplishments and challenges overcome in this project, we will describe each block in detail. In researching circuit breaker technology, we came across two main areas. The first being mechanical switching, as you see on the right, and the second being solid state or electronic switching, as you see on the left. The main differences between these two are the fact that solid state circuit breakers switch much faster, with times being in the microseconds, while mechanical circuit breakers can take in the milliseconds. You may think this is not that large of a difference, but that's about 3,000 times faster. Another big difference is the fact that solid state circuit breakers, as the name implies, are one piece. There's no moving parts. There's no connections that are going to physically open and close, such as the mechanical circuit breaker. And because our system is very reliant on being rugged and being able to take vibrations and moving, as well as being reliable and having a fast response time to any outages, solid state circuit breakers are the technology that we moved forward with and are going to implement into our system. So next up is our power monitoring system. On the left here, you can see our basic communication architecture. We're following an SNMP protocol. And basically, if you look a little closer at the individual components on the bottom, they each have an MIB, which essentially stores the data and information that is being read from the components, such as power levels and voltage levels. That's communicating with the SNMP agent that then sends and receives messages from the SNMP manager, and then the manager is communicating with the interface, which is basically how you control the system and read information from the system. And all the connections within that are going to be through fiber optics. So now moving on to our software here on the right, we're first going to be using DCIM, which is Data Center Infrastructure Management. And this is kind of what provides the data and gathers a lot of information for us. And then in combination with BMS, which is Building Management Systems, this is kind of what would be used to take action on the data, or the control side of things. And adding both of these together, we receive an integrated monitoring software, which is what we hope to develop in this project. Continuing with the power monitoring, here I just have an example of a system developer that we've been interested in, Sunbird. So on the left, and you can see in this screenshot, essentially some graphs and waveforms of things being measured, such as power and load of the transfer switch, showing, up in the big red, you can see failure. It tells you which components are running fine, which components are not running fine. And on the right here, we have a different view of this system, which is kind of a 3D model where you can go in and build your data center, very customizable, and gives you a nice view of your system rather than just having a screen with charts and graphs. One of the most important pieces of technology in this system is the PDU. So in our system, we have two types of PDUs being implemented. We have the main PDU, which you can see here on the left, which is where the output from the DC output from the UPS is coming in. And then that is going to then distribute power to a rack PDU in each rack. And so these racks PDUs are essentially going to be switched, which means that we have the remote ability to turn on and off individual outlets, as well as receiving data on what is going on in each individual outlet, such as power draw, current levels, and as well as giving us the capability to see any type of fluctuation going on. So on the top here of these diagrams, in the red and the blue, we can see the different types of cabling that's going to be running. In the red is our power path, and the blue is our fiber optics, which I mentioned earlier, that is going to be used for communication rather than just having a wireless system. And to hold these cables on top of our racks, we're going to have some type of um, metal cable trays, whether it be one tier or two tiers, to kind of keep all of our cables and wires out of the way on top of our system. The main technical accomplishment that I would like to complete by next semester is the simulation and modeling of our components in MATLAB Simulink. A couple important components include solid-state circuit breakers, our power monitoring system, and other components that we deem necessary to simulate as we continue our research into next semester. So this is going to be one of the most important parts of this project, as it will allow us to find out the capabilities of our system and see how our developed system really reacts to, varying conditions in the power.
Hello, I am Alexis Noriega, and I'll be going over my research into UPS systems, battery technology, cooling systems, and transfer switches. So a UPS is an uninterruptible power supply, and its main function is to provide a safeguard against power failures. These are a key part of a data center as they will protect critical systems from shutting down abruptly and potentially corrupting data. To the right is a system where two power feeds run through a transfer switch and into a UPS, which charges the battery and provides power to the load. Two types of UPS systems are double conversion UPSs and delta conversion UPSs. A double conversion UPS functions by sending power through a rectifier, converting into DC to charge the battery, and then through an inverter, converting it back into AC to power the load, and this is shown in the top right. These also include a bypass in case of need, and typically double conversion UPSs offer better efficiency than most other UPS types, and they also offer no transfer time between switching. Delta conversion UPSs were introduced to improve the slight drawbacks of double conversion UPSs, and these include a delta transformer before the rectifier and have an even higher efficiency, and they also reduce power losses. What we opt for is a complete DC system. So what this means is that our UPS will run utility power through a rectifier to power both the load and the battery. This would mean there's no need for a bypass, as power would follow the same path in any circumstance. And the great benefit of this UPS system is that it should improve power quality and allow for greater scalability, as DC power is easier to work with. And this is due to the fact that less components are needed and there's no need to worry about harmonics, load balancing, and other drawbacks of AC power. Battery technology is important in the data center as they are what store emergency power in case power fails. Nickel zinc batteries are promising as they are safer than the standard lead acid battery, and they typically have a longer operating life of up to 15 years. Another benefit of these is that they remain conductive even when they are depleted or weak, which results in increased reliability and less maintenance need overall. Another promising technology is supercapacitor batteries, in which their strength is their ability to charge and discharge very quickly. If runtime isn't a concern, supercapacitors are a great option for a battery. And these can also be used in addition to a battery, where you would get the battery's long runtime with the supercapacitors fast charging and discharging. And this will make for a very big improvement from a standard lead acid battery. Cooling technology is vital in a data center as proper cooling for server racks prevents critical systems from overheating, and this allows them to function smoothly and without interruption. One form of cooling is direct switch cooling, and this is a great option as it is one of the most efficient cooling techniques. It uses a non-flammable dielectric fluid for cooling, which goes to a component's cold plate and cools the processes directly. The liquid is then extracted and sent to a facility's chiller plant to be used again. Transfer switches are an important component in data centers as they are what allow for the seamless transfer between two power sources. Two types of transfer switch are static and automatic. Automatic transfer switches use a switcher mechanism to switch between power sources, and these typically have several configurations such as close and open transition, and use several switch mechanisms such as those in contactor and power frame type automatic transfer switches. Static transfer switches are an electronic circuit structure, and they typically use a semiconductor to monitor power. Since these don't have any moving parts, they don't need nearly as much maintenance as automatic transfer switches. And another benefit of these is that they offer very high switching speeds, which makes these a more favorable option for use in data centers. So building a prototype of our system and testing its functionality is something that I would like to complete by the end of the next semester. And this will include setting parameters for a physical test, determining what components are needed for testing, and deciding a method of how I will test and measure results for the system. Some remaining technical accomplishments we still require are developing a full concept model of our system and finalizing the design, as well as making sure components work well together. To do this, we'll plan dates for completion of testing for components, and we hope to finalize this plan by February 1st. We will also continue our research on new technologies and review technologies we have already found to help us in finalizing everything necessary. Other technical options we hope to complete are our prototype testing and our simulations. We hope to show that our system is superior to others with the results from our testing, as well as show how our design works in our simulations, including how it responds to various scenarios a data center might experience. One risk we considered in our project is that we choose a component that is outdated by the time our system is implemented. The impact of this would be that our sponsor company would have the same problem they do now. We gave this a medium likelihood, medium seriousness, and overall grade of C. And our mitigation strategy is to be as forward-looking as we can with the technology we select. Another risk we had is that MATLAB Simulink might not be powerful enough on our laptops to run necessary simulations. The impact of this will be that we'd have delay in getting those simulations, as well as in our entire project. We gave this a low likelihood, medium seriousness, and an overall grade of D. Our mitigation strategy for this is to gain access to a more powerful computer, or find another application that would be able to run the necessary simulations. Our third risk is that we choose a component that doesn't meet the readiness level to be available when our system is being implemented. And the impact of this will be that our project could be delayed and thrown off schedule. We gave this a medium likelihood, medium seriousness, and a grade of C. And our mitigation strategy is to spend a good amount of time analyzing readiness levels of each technology we choose when we are conducting down selections. We would like to thank our technical directors, Mike Brauner and Tyler Bogson, for their guidance and for their help throughout our project. We would also like to thank Mike Smith and Dr. Sunak for their additional help in the Capstone program. Thank you.